Hello, hello. Welcome. Oh, there are a few more people coming in. Come in, come in. It's not too late to join us. Hello, my name's Kris Jenkins. I'm a developer advocate at a company called Confluent. And I guess I'm going to start with explaining how I came to be one of those. Because for years I was a developer. I was actually the CTO of a company I founded, and we were a Java shop, and we ran mostly Java for 10 years, and it was great, and we were all happy. And after working there for about 10 years, I decided it was time to move on and do some new things and learn some new things. And by a weird roundabout route, I actually ended up spending about 5 or 6 years mostly building event-driven systems and event-driven architectures, mostly in Haskell or Clojure, which are really esoteric languages, but that's the way my life went at that time. And I really like them, and I will talk your ear off about those languages at length if you like, but that's not this talk, so you're safe. But in all that time, I was building these event-driven systems based on languages that are deeply rooted in immutable data and streams of data. In all that time, I never found a database that really worked with that way of thinking. Never one that I was happy with. And I usually ended up defaulting back to Postgres because it didn't quite fit with event streaming, but it's a great database, right? So if all else fails, it's a great choice. But then a friend of mine encouraged me to try Kafka. And I thought, well, what's Kafka? And where does that fit into things? Because is Kafka a database? No, it's absolutely not a database. Everybody knows what Kafka is, or if they don't, they soon find out that it's kind of a fancy queue, right? Stuff goes in, and it travels along, and it goes off, and then that's the beginning and end of Kafka to some people. I think that's terribly underselling it. It isn't a database if you see it that way. But Kafka definitely is a database if you see it in another way, because what's a database? It's a relational thing with sets and cod and fourth normal form, if anyone ever actually uses that and all that stuff. Databases are things like MySQL and Postgres and Oracle. But I think we've got a broader picture of what a database is these days, because we now accept generally that key value stores are databases, right? Or document databases, they're still databases. Is Git a database? I would argue that it is. It's a database. Is blockchain a database? No, too controversial. I should step back from that word. But we have a broader definition of what a database is. In fact, I'm going to give you a quick, informal definition of what I think a database is. If you can store structured data reliably and query it out in multiple interesting ways, you've got a database. Kafka definitely fits that definition. So if it's a database, the question becomes a far bigger and far more interesting question: what kind of database is it? What is Kafka's nature? What, we might ask the Zen master, is the Kafka way? That's a very abstract question, and I only have one way. I only have one way of answering abstract questions, which is to build software, to write something, to get my hands dirty in it, build something up, and then step back and say, what have I built? What does this thing actually look like? So I thought I'd do that. I did this as part of figuring out what Kafka really is and what kind of database it is. And I thought, what shall I build? Okay, there are 1,000,001 Java pet stores. I hope we've just kind of got sick of Java pet stores. I don't know where that keeps happening. If you go from Java to JavaScript land, there are 1,000,001 to-do list managers, so I don't think we need another one of those. If you live in the event streaming world, there are 1,000,001 order processing systems. That's kind of a bit of a cliche now. So I thought, what can I build? What can I build that would make for an interesting, complex event streaming system that I can kick the tires on Kafka with? I thought I'd go for a text adventure game. Thank you. Now, there are some of you in the audience, like my friend here, who think of text adventure games and have very fond memories of years gone by and hours gone by. Some of you don't know what a text adventure game is, so I'm going to give you a quick history. They kind of survive today as narrative adventure games. Right? You can find these on Steam today, where you go around the world and you talk to people, you make some decisions, and the plot advances by which decisions you make and who you talk to and where you go. Before then, we had another golden age of computer gaming, which was The Secret of Monkey Island. I knew you'd like that. Yeah. Which is the hours I lost to this, swapping floppy disks to get the thing to load. And this is a game where you point and click your way around the world, and you find items, and you pick them up, and you use them somewhere else, and there are puzzles, and the game advances like this. Before the glory days of The Secret of Monkey Island, we had games like this, which are mostly text with a few high-resolution graphics. I thought I'd build something like that, but I thought I'd do it I thought I'd cop out and not have the images. I'd just go with text. So let me give you a demo of what I built, and then we can talk about how it's built, and that's the important thing. Live demo. Are the gods with me? Let's find out. So, can everyone see that? Let's make it a little larger. You good at the back? Yeah, everyone happy. Okay, so, how do you play this game? Let me just type some junk and see what it says. Unknown command, sadf. Try asking for help. Okay, that's promising. Help. Available commands are look, go north, south, east, west, pick up an item, use an item, inventory, and the help we just asked for. Okay, look. You are standing on stage at Jfokus. The audience bask in the soothing glow of a terminal window. In the corner sits a computer noisily spitting out data. It needs to be processed, but you have no idea how to do it. Okay, let's try one of those direction commands. Where should we go? Let's try going west. You step into the toilets. There's nothing to do here, at least nothing I want to describe. That was a bad choice. Let's go east. We're back there. Let's go. Should we go east again? You're backstage. An old rock band is hiding here, refusing to go on. Is that a reference to Dylan from this morning? I don't know. You look at their equipment with envy. You can see a microphone and a guitar. This hasn't worked out very well. Let me go back to where we were. Okay, you can see data and a lanyard. Well, this is why I named the talk what I named it. Let's pick up that data. You pick up data. And I check my inventory. Your knapsack contains data. How ambiguous. Let me pick up this groovy lanyard I've been given. Let me pick up a lanyard. Okay, is that in my inventory now? It should be. Your knapsack contains data and a lanyard. Okay, let's try going north. You enter the main hallway. It is bustling with life and coffee. Okay, let me try using my cat. You do not have that item to use. Good, that was a test, it works. Okay, let's try using the data. Can I use the data here? You cannot use that item here. Okay, last try. Let me try using that lanyard. You wave your lanyard in the air like a fool. Someone in the distance shouts, hey, that looks like fun. And pretty soon you've started a flash mob of lanyard wavers. You dance for hours, and then the party subsides, and as the mob leaves, one dancer drops his conference t-shirt. You pick it up, and your knapsack now contains data and a t-shirt, and the lanyard's gone. And that's how these games work, right? You wander around, you find some things to use, you wander around some more, you use them, and gradually the story unfolds. And usually the last item you pick up is the magic token that says you've completed the game or something. That will do for the demo. Let's see how it's built. Yes, there will be source code at the end if you want it. Brief warning before we get into the code. There is a lot of code in this, and I put a decent amount of code in the slides for a couple of reasons. One is if you're watching the live stream at home, you might want to pause it. If you're watching the live stream back in the future, if you're in the future and you're watching the live stream back, then you can pause it, which also applies to all of you in the room, should you want to go back and take notes. But also, it's our common language. Thank you for using English as a common language. I would have no hope otherwise. But our other common language is code, right? So it's a good way to communicate. But I will say, don't get lost in the code. The most important thing is the shape of the code. Don't get lost too much in syntax. Just let it wash over you as we're approaching beer o'clock. So just get the shape of it. Okay, so how did I build this? I started out by building a very, very, very thin web server that would and a fairly simple client, which you've just seen, that would just do something like this. I send a string across a WebSocket to the server, and the server writes it to what's called a stream in Kafka land, which is just this infinite list of event data. It's an immutable infinite list. Data streams, data streams through on this command list, and then we have to do stuff such that we put a response on this response stream, and our dumb, thin client will spit that back out, right? And when I built this, I literally just put up the front end and a web server that could do these two things, send stuff to my command stream, read stuff from my response stream. I pretty much left it running because all the magic is inside do stuff. So what do we put? Oh, before we get to what we do, put in, I told you there'd be code. There's a little bit of code. So I've just, this is it in KSQL, which is a variant of SQL for Kafka. The streams are almost identical, commands and responses. The one thing I added was a source field on the response, because it was handy for debugging. But they're pretty simple, right? It's just a raw string going in and out. So let's do some stuff. What stuff should we do? Well, let's get started. We'll build a very simple echo server. If you've ever built like any kind of networking server, it's probably one of the first things you build, right? The echo. Something like that. So let's do that in code, and we'll check that the whole round trip is working, and then we can start to build the game. In code, that would look like this. I'm using Java streams here. There's a version available for Scala, if you like that. We just say, give me a stream building object, and I would like to create a command stream which is streaming from a stream called commands, right? Read the commands and just let me treat it as an infinite stream of data. There is some serialization stuff. I'm leaving that out of future slides. So let's read it like this. Consume those commands with some serialization stuff. Check the source code if you want all the gory details. With that, we can now build our echo server. And it's just going to look like this. Take a command stream and map this function over it. If you're familiar with Java streams, you're probably happy with the idea of mapping stuff. If you're not, it works like this. I'll give you a function that can deal with one piece of data. You turn it into a function that can just work on every piece of data in the stream. It's a building block of functional programming, stream programming. So we teach it how to deal with one command, and the way it does it is just by prepending, I love the word prepending the word echo. Okay, once that's working, and just to prove it, I've got a filter here, and if I stick the echoes in, you can see those. They're all actually happening in this demo. I just filter them out, and you can see all the different sources we're going to go through to get there. So, with that, we can start building the game. This is where it will get tasty. Everybody with me? Good. So we need the supporting commands like help. We need to be able to move around a map, and we need to be able to deal with items. If we can build those three things, we've got a game. So the first thing we want to do is figure out which of those kinds of things we're dealing with, right? And we've got this support in our nascent stream processing application to say, look at each command, and if it matches these criteria, I'm going to handle it in this way. Otherwise, someone else can worry about it. It's like a if, else block like that. If you're going for a job interview and you see this, call it the chain of responsibility pattern. You'll get hipster points for doing that. So, in Kafka streams in Java language, that looks like this. Take the stream of commands we've already dealt with and split it. And that will give me a different object which I can register handlers of different kinds in. The first and it will look like this. So I'm going to get the key and the value, and I'll return true if I want to handle it. And for the things that it returns true, I get to write some processing code. So here's our first real command. If that command is the string help, then map values over that for every one of those, build a response string. And it's long, but it's the help string you saw, right? And we just spit that out to the responses string. And with that, we've got help handling. The other thing we can do with this split stream is we can say, let's define a fallback handler. Let's define a final else. And that final else will only fire for all the stuff we didn't handle somewhere else. And we can make it look like this, unknown command, and then just echo back what the unknown command is. So with those two things, we've got help and we've got, I have no idea what you're talking about. And we just need to put all the stuff in the middle to build out our application. So, how do we do that? Well, let's start, before we get into actually processing it, let's do a little bit of routing. Let's say, let's grab all the movement commands and let's grab all the inventory commands and just send them on for forward processing. So I did this. I'm doing it in two ways to show you the two different ways of doing it. There are probably more. Two will suffice. Take a list of all the valid directional commands. And if you're in that list, I would like to deal with you as a movement command. But I won't do it here. I'm just going to stream it off onto a separate stream to be processed by someone else, perhaps by another microservice. In the case of this code, it's kind of by a microservice that's running in the same JVM, but it doesn't matter. Stream it off to a place called movement commands, and that's it. I've dealt with it here. I'm not going to think about it anymore. I'm just routing. Or I could do something slightly fancier. I could still just do routing, but I could try and get some structure into this. So I wrote a parser that will split out, will look for and split out the different inventory-related commands, right, into a more structured object, into an inventory command object. And if that parser can handle that, then take the raw string, split it into an action and a noun, verb and a noun, and pass that off in a structured way to some inventory commands. So I'm routing it, I'm enriching it a little bit, but I'm not actually handling it, not actually processing it here. I'm just moving it on. So we end up with something that looks like this. If we can fill in those downward chain bits, we'll have an application. Okay, so movement. Let's look at movement. This is the first really tasty bit. How do you deal with movement in a system like this? You're going to get a series of commands like go north, go south. And what you'd ideally like to end up with is a table that has a user ID and where they are right now. That's kind of what we're trying to get to. So I can look up someone's user ID and I can say they're there. So, bit of pattern matching to change from the string to XY coordinates. I'm doing X is... So north is X, there's no change in the X, but the Y goes up by 1, yeah? If you've ever programmed a 2D game, you've probably used this kind of coordinate system. A little bit of null handling at the bottom, because this is Java. And then I can take that stream of not commands, but deltas, and I can say, you need to group that by user for this to be meaningful. And then I can reduce it. I can say, as the new ones come in, add them to a kind of rolling summary. Again, if you've used streams libraries, this shouldn't be too wild. If you haven't, we're just adding those deltas in per user as we go. Any Haskell programmers in the room? None. Okay, this is a monoid. I'm just going to say that. I gave this talk once before, and I asked if there were any Haskell programmers in the room, and no one answered. And then at the end, 2 people came up to me and said, I'm a Haskell programmer, but I didn't want anyone to know. So if there's one of you in the background, I'm with you. I'm with you. So we've got this rolled up position, this table, which is interesting, because a while ago it looked like a fancy queue, but now it's starting to have tables, and it's starting to look more like a database, I would say. The interesting thing, the thing I really like about Kafka's tables is they also behave like streams. They also behave like real-time sources of events. So I can take this table which I've rolled up of where everybody is, and every time it changes, I can get a new event, a new piece of data telling me that the person's moved. And so I can use that, I can map over that position table stream changing to tell people if they've moved. And again, I actually do that in the app. If I put that in the filter, yeah, can you see that? You've moved to position, blah, blah, blah. But when I got to that stage, I realized that's actually not enough for an interesting game. You need locations, right? Just being told you've moved to an XY coordinate, not terribly exciting. So how do we fill in the map, right? We kind of need another very familiar database-ish thing, which is an idea of standing data. So I created a stream of location data, where X and Y are the key, and there's a description, and there are some objects, right? And I did some insert statements. You're on a bridge, you're in a forest, you're at home with your television and fish, which sounds like a lovely home to be in, right? And then I did the same trick I did with positions. I rolled this up. Into a table. I'm not going to get too much into the details. There are two kinds of tables in Kafka. There's one that's sharded for spreading out, for wide processing, and there's one that's copied on every node. And this is the right choice, a global table. I need that map data on every single node if I've sharded out, but it's small and it's not going to change much, so that's fine. That's a detail. So now this gives me two tables, right? I've got the user's position, and I've got a position and its description and objects. And if I could join those two together, I'd have a richer position message. I'd have not just where you've moved to, but what you've found there. So in code, that looks like this. Give me the user's position table and turn it into a stream. So every time it changes, I get a new piece of data to deal with. And then do a left join, because there might not actually be anything at that location. And if you took out the null handling in this, it would basically say, I'll give you the user and their position, give me the key for the thing you're joining to. That's easy, it's the position. And I can just mash that data together with null handling to get a richer object, which is the join of those two things. And then I can map over that and say, every time that thing changes, send that richer piece of data on to the end user. And I've got some null handling to say you've fallen off the edge of the map, and that will have to do for now. It's not that big a game yet. If we stop there, we've actually built a walking simulator. Not my favorite kind of game, but there are games, you'll find them on Steam, walking simulators where you just walk around and read the story. Never quite got them. If anyone likes them, please recommend a good one to me. I don't think we've got a game until we've got some puzzles to solve and some interactivity. So let's do something like that. Before we do it, I've got a feeling that that richer stream of user moving around will be useful. So let's turn that into a table too. We'll group it by the user key, and this time, instead of reducing it by adding them together, we'll just throw away the older one. So every time this changes, we keep the newer version. That will give us a rich table of where they are and what they can see there. This will be good. So, just pause there. We've got live streaming data coming in and spinning around and going out and being processed. We know how to fan data out and hand it off for later processing. We've got a notion of standing data. We have stateful tables, but the stateful tables themselves can do live notifications and rejoin in that stream. And we have joins. Quite a lot so far. It's a weird database, but it looks like it's certainly a data processing platform. Okay, so inventory. This is where it gets tasty. How do we handle inventory? You need to be able to pick things up. You need to be able to see what you've picked up, and you need to be able to use it. Picking things up, let's try it like this. So I've got this table of where they are and what they can see in that place, and I'm getting a stream of pick up X commands. So I should be able to use that to either send them a rejection message or successfully grab it and stick it on a stream of inventory messages. Right? That's going to look like this. Take the stream of inventory commands, which have been parsed and enriched and routed from earlier, and then join them to the user's location, so I know what they can see there. And I take those two things, where they are and what they can see, where they are, what they can see, and what they want to pick up. And I say, is this item available? And I send that on as a kind of pickup object. So it's going to say what they want to pick up and whether or not they can. That'll do for now. I'll ship it on for forward processing. With that, I can then split that and say, well, first handler is it available? If it is, I'm going to stream off a change of their inventory. I'm going to say they're picking up this item. It's now held. That's true. And stream that off to a stream of inventory commands. My fallback case is it's not true. Default branch, you can't pick that up. And I just stream that off as a rejection. Okay? But I should also, so if they pick something up successfully, it goes onto the inventory stream. If they fail, I give them a response. I actually need a second handler here to let them know they've picked it up successfully. So I should start watching that changing stream of inventory things. And I should say, if held is true, if they've added a new thing to the stream of things they've picked up, then just send them a message, stream that back to the responses. So I'm processing that inventory in a couple of ways. Okay. Onto the knapsack, the bag of holding, where you put things in. How do I now now I've got this stream of you are holding true, you are holding false. How do I turn that into an actual inventory object? Like this. Take that stream of inventory commands and group it by the user ID. And then, again, I sort of want to add things together and produce this roll-up. But it's not exactly the same as a reduce, because what I want to do is take an empty array and add in every change, right, as it comes along, and return a new empty array. If you're used to functional programming, you probably know this as a fold, but it's pretty simple. All I need to do is say, I'm going to get the user's key, the item they want to deal with, and the previous knapsack, and I need to return the new version of the knapsack. And this would be super simple if the Java APIs were a little bit more friendly. It's not. Adding stuff in is super easy. If the item they're holding, if the item is now held as true, and they don't already have it, then add it into the array. If it's false, then we need to take it out of the array, because that's how we process people dropping things. And the Java API is pretty horrible for this, but it's just array remove, okay? So we're just reacting to that true-false flag and either adding it into the array or removing it. With that, folding over that stream of inventory changes, we should be able to deal with inventory commands and tell people what they've got. So look through the inventory commands for something where the command is inventory, which you type in to get the check. Join that to this table of knapsacks, which is going to be the user ID and the array of what they're currently holding, and just print that out nicely. Okay? Which brings us on to the last piece, using stuff. How do items work in this? We're going to need another standing data table, I think, and this is a rules table. The key will be the source item, the thing they're trying to use, and it will tell you where you can use it as an XY coordinate. When you use it, what piece of story do we spit back out to the user? And what new item does using that item generate? So, for instance, we can insert a drink, and there's a description when you use the drink at 5.8, and you get a glass back, an empty glass. Let me demonstrate that now live. That wasn't planned, I was just thirsty. Okay, so again, we can do this trick of building up a global table. There aren't that many rules. Let's have them on every node. And then we need to do something like this. All those requests to use something, we're going to need to join to your knapsack so we know what you're holding. We're going to need to join to your current location so we know if you're in the right place to use it. And we're going to need to join to the rules about items to see if this item can be used here. And if we have all that, we can probably finish off writing the game. So it looks like this. Take that stream of inventory commands and filter for the stuff where the action, the verb, is use. Then join that to your knapsack so we know what you're holding. And I've got an intermediary object. I think I used the Java tuples library for that. It's quite nice if you don't know it. Handy for intermediary objects. Probably wouldn't use it for something more domain permanent. But this isn't going to last long because we're about to do this. We're about to join to the user's location, another intermediary object. I have no idea what it's called after you get to triplet, quadruplet. I don't know, I don't care. And then left join to the item rules, and we'll return a more structured object now, a use item join, I'm calling it, and it looks like this. It tells us all the data we need to know from those different sources that will let us process the command and we'll be finished. So let's process it. Take that stream of use item joins and deal with you don't have it. So see if it's available in their knapsack, and if it isn't, return this message. You don't have that item to use. Next possible case, check if the X and Y of where you are matches the X and Y of the item's rule. You're in the right place to use it. If it doesn't, spit out you can't use that item here. If we get past those two cases, we should be able to use the item. So our fallback branch is, let's do two things actually. Let's tell the user that we've processed their use. So we're going to give them the description for when they use this item. And we'll do the inventory change. And there are two slightly interesting things about this code here. One is that we can, in the same place, we can react to one change and spit out two different messages. So we can spit out a new responses and a new inventory message at the same time. The other is, in this inventory change, we're actually spitting out two sub-messages. We're saying the item you were holding is now false. It's now no longer held, and our knapsack will drop it. And the item that we generate from this rule now goes into your knapsack. So I managed to fit this all on one slide. Hope you're happy with that. But we end up, I think that's it. I think that's it for the code. We end up with a system that looks kind of like this, right? Data's coming in, and as each piece of data comes in, we react to it in some way. We maybe transform it into a different piece of data. We maybe put it onto another stream of data for someone else to handle, maybe in the same Java process, maybe in a separate Java process, maybe sharded. But the data comes in, we do something with it, and spit new immutable data out. And that is the whole of the application. You can reduce it down to that one idea. Data comes in, make a decision, make a transformation, spit the data out, and on it goes. And we're done. So now we get to the point where we get to step back from the thing we've built and ask ourselves what we've built. And the first part of that is saying, is this just a toy? Am I just playing? Yes, but also no. Sometimes my job is to convince my employers that I'm doing serious work when really I'm mucking about. Sometimes my job is to convince you I'm mucking about when actually this is serious work. Because if you squint, if you look at this in a different way, that inventory system is actually a shopping basket, right? Customers come in and they add stuff to their shopping basket and they take it out. And we may wish to track, we both definitely want to track the current state of their shopping basket, but we might also want to see what they added and removed and nearly bought but didn't quite. If you look at the item rules for what you can use where and what it does, it starts to look quite a lot like a workflow system, right? There are rules about how you transition from one state to another, and if you satisfy those rules, you get into an entirely new state. You can see kind of how you would build up a workflow system from this. You can look at, as we enrich the user's position with a description of the location, you can see how that would start to go into things like parcel tracking. As it moves around the world, enrich that piece of data with information about the location that parcel is in. You can look at just the process of tracking the user moving through the world, and you start to see analytics as they move across your website. You can use all these same techniques. Data comes in, make a decision that causes you to spit an onward piece of data, and build up all these kinds of applications in different ways. And that makes me want to step back and see the bigger picture than that, which I think is really happening in our industry at the moment. And I'm very interested in it, and I like it, and this gets back to why I'm working for Confluent. I think there are at least two big answers to the question, how do we manage complexity in systems? One of them, which really came to popular prominence, I would say in the late 90s, was the idea that the way you deal with complexity is you build an object, and you put a wall around it, and you say, if you want to access this complex, stateful thing, talk to me, I'll do it for you, and I'll respond. And then the game becomes having all these different islands of state talking to each other. And that's the new complexity you have to manage. The alternate way, which is probably just as old, but it's only just now starting to become popular, I think largely because memory is getting cheap and parallel processing becoming more important. The other way is to say the way we deal with complexity is firstly, you eliminate it. You don't have mutable state in so many places. You have immutable data, and when you make a decision based on it, you spit out another piece of data. And the game becomes taking in data and transforming it into new data and building up these graphs of assertions and conclusions, you might say. And I think we're seeing this shift everywhere in our industry, and I'm not really advocating for one or the other, but I'm definitely advocating for knowing both. If you take this idea of going from mutable objects to immutable state with transforms, then you see the rise of functional programming languages, Haskell, Clojure to a certain extent, Scala, F#, that'll do, that's a good list. Good list of the idea of taking in data, transforming it, and doing something else, right? If you take the same idea and go into the world of user interfaces, then you have the shift from something like Angular 1 or jQuery manipulating stateful parts of the page, and instead you go to something like Elm, which I built this in, or React and Redux, or RxJS, where stuff comes in, and we don't change the stuff, but we make decisions based on the stuff and spit that out to the page, perhaps with a virtual DOM. So we have this nice thing in React, for instance, where stuff comes in, it changes our roll-up table, our state, and someone else can worry about rendering it to the screen. I think you also see this a bit in DevOps, right? We used to manage individual stateful computers, and now instead we have this recipe, like maybe a Docker file, where we say, starting state, here's a list of transformations you can apply to the starting state, and that will give you the final state, and we don't worry about that. It's just data and transformations. It's a very interesting and rising paradigm, and I think you see it everywhere. And if you want to see it in the world of databases, you will see it in the move from mutable tables to immutable streams of events and different ways of processing them. And I find that very interesting. I spent a long time thinking about those ideas in the programming language world. I'm finding it very interesting to think about it in the world of databases, because those are big and they span entire companies. So I encourage you to learn more about them, whether it be in programming languages, DevOps, front-end design, or databases. And I'm about to wrap up. Pause. That's pretty much the big idea. If you're interested in this, I have got, shameless plug, I've got a video coming out this time tomorrow, actually, where I do a complete walkthrough building something in a system like this. It's going to use musical instruments and 3D graphics engines, TypeScript, and a bit of Kafka. Maybe don't watch it because you're busy here being at Jfokus, but I hope you'll watch it sometime soon after. If you want a link to that, or a link to the source code, or a link to the podcast I host, or, there's a QR code. These are great. It's got all the stuff on there. And with that, I'll stop for questions. Thank you. Yes, hello. Okay, yeah. So which one was that? Anyway, at one point I've got, I define a table where the key is the XY pair of your location. Under the hood, that's just going to serialize them and use that serialized version as the key. So it's a composite key in database terminology. No, so the underlying topic on disk, it's going to look like a key and a value. And the key in this case will be the serialized pair. Yeah, okay. Any other questions? Hi. So the question is, how would the performance be? There are a few pieces you need to understand to describe that. The first is it's dealing with data and pretty much processing it straight away as it comes in, right? So it's not rolling across this stream of events every time something changes. A new piece of data comes, it reacts to that one new piece of data, and the answer comes in. So the performance generally is more, the performance doesn't really change as the number of events grows. What does change is the latency as the number of different stages you've got, but that's generally quite fast because the delay is dealing with one piece of data. I didn't go into it in this talk, but there are nice ways of sharding out the data by key, so you can say, I'm using UUIDs as my user ID here, so I might very logically split it out by the first character, which gives me 16 shards. So I can run this game over 16 different computers fairly trivially. And I'm looking forward to the day when I have that many players. That would be nice. I would happily talk to you more about performance, but generally it's pretty easy to scale horizontally. And latency is more of an issue than processing, I would say. To give you a benchmark, I know Honeycomb use Kafka, and I think they do something like, the last I heard it, they were doing 2 million events a second. I know that's gone up, I don't know what to. Any other questions? Any Haskell programmers want the last chance to raise their hand? Stop fishing, it's never going to happen. Okay, thank you very much.